Alright, what's up everyone? Welcome back to Structure Free Learning. In this video, we return to our structural analysis sequence, and in particular, we're going to focus on explaining the moment area theorems, the dreaded moment area theorems, which really are a nice way to calculate the slopes and deflections at different points along the length of a beam or along the length of the frame, as long as you can acquire the moment or really the curvature diagram of the structure. Let's start by taking into consideration a simply supported beam with a uniformly distributed load. And let me also establish a coordinate system for this so that x is going to the right along the length of the beam. And my deflection is considered positive upward. So I have my origin at the left support. One of the first things that we have to do is apply our basic statics, calculate reactions, draw the shear diagram, and draw the moment diagram. Here, the moment diagram for this simply supported beam would be parabolic and would look something like this. And if my beam has a constant EI, or flexural rigidity, then to generate the curvature diagram, the M over EI diagram, I can just straight up divide the moment diagram by EI. And this will have this, this curvature diagram will have the same shape as the moment diagram, but just shift down based on the value of EI. Now I want to take a closer look. Let me erase this over here. I want to take a closer look at my deflected shape when I talk about the first moment area theorem. So the deflected shape will look something like this. And if I look at 2 points along the length of the beam, let's say I take this point as point A and this point as point B. From the deflected shape here's the tangent line, and here's the slope, this going downwards, if you will, rotating clockwise is theta A, and here rotated counterclockwise from the horizontal is theta B. So the first moment area theorem says that the area under the curvature diagram between 2 points is equal to the change in slope. So what it means is this area is equal to the change in slope, or the difference between theta A and theta B. And the way that we can prove this, is from the moment curvature relationship, which is that d squared v over dx squared, the curvature of the beam, is equal to m over EI. And this d squared v dx is also just the derivative, or the curvature is the derivative of the slope, which is m over EI. If I set this integral up, if you will, this d theta is equal to m over EI times dx. And just from basic calculus, this would be theta A to theta B, and this would be from point A to point B. And this tells you that the change in slope from B with respect to A is equal to A B m over EI times dx. And this is really the first moment area theorem. Now for the second moment area theorem, let's consider the same simply supported beam, same curvature diagram, and this time for the second moment area theorem, we're looking at vertical distance between tangent lines. And what it says is that the vertical distance to a point, in this case point B, or the tangent line at point B, from the tangent line at A is equal to the first moment of area under the M over EI diagram. And so what that looks like is this. So here is the tangent line at A, and here is the tangent line at B, and this vertical distance, which is often used TB, which is basically the vertical distance to B from the tangent line at A, this TBA is the first moment of area. Here is this red shaded region is the area, is equal to this x bar, the centroid, the first moment of area of m over EI times dx, where the integral is from A to B. And in this case, x bar is defined as the distance to the centroid from point B. And if I wanted the vertical deviation, or the vertical distance to point A from the tangent line at B, this would be TAB, this would be equal to x bar prime A to B m over EI times dx. And that would be here. Now this is really useful in calculating the vertical displacement at different points along the length of the beam, and you don't really have to apply the integral. Normally the moment or the curvature diagram is enough or geometry friendly enough where you can just break it up into areas and multiply it by the distance to the centroid of that area and sum them all up. The rest of this video I'm going to explain where this comes from because some of you may not believe. And so in order for me to explain where this comes from, let's take a closer look at this AB. I'm going to draw an exaggerated deflected shape, and here is point B, point A. And where this comes from is the idea of shallow curves. We call this distance right here, we call that dx, and we neglect the slight curvature that it actually has. And if you recall from way back when, probably in mechanics of materials, you derived a relationship for the curvature of a beam based on the geometry. And if this distance right here is dx, and we said that here is this radius of curvature rho, this angle was d theta. Using a small angle approximation, we said that rho times d theta is equal to dx, and this said that this d theta over dx is equal to 1 over rho, which we called curvature. And if you believe this, you're halfway there. And the idea is that here there's this tangent, this vertical deviation, and if I draw from this point here, the tangent at that point, the front of dx if you will, there would be a slight line like this, and then the tangent from this point right here, which would be right about here like this. And the idea is that this angle is approximately d theta. This distance we're going to assume is small enough that we can take it as vertical. And that's based on the shallow curves and small angle approximation. And we're going to call that dt. And this distance to the first point, I'm going to call that x. And the idea is that, again, with the small angle approximation, the idea is that this dt is equal to x times d theta. And if you recall, we said that this d theta dx is equal to m over ei. And I can substitute into here this definition of d theta, which is x times m over ei times dx. And if I sum up, or if I integrate over every little increment along the length between a and b, I would have from a to b dt is the integral x dot m over ei times dx from a to b. By this relationship, I would get that the vertical deviation to point B from the tangent line at A is equal to this integral AB, or basically what this is the first moment of area, which would be x bar, the centroid of that area, times m over ei times dx. And this is the second moment area theorem. Alright, so hopefully that gave you a sense of where the moment area theorems come from. In the next few videos, we'll do a bunch of application examples and just how to implement the first and second moment area theorems to really calculate the deflection and slopes at different points along the length of a beam. Alright, let me know if you have any questions. See ya.